Hey, everybody, welcome. This video is going to be discussing the definition of the integral. And you should have already watched the introductory video on integration if you're watching this one. If you don't know about that or haven't seen that, please watch that one first. So basically, definition of integration. So in the previous video, we discussed that really all we're doing is we're taking a function, we're evaluating it, we're multiplying it by a width that generates a rectangle, we're adding those rectangles together. Okay, so just a quick little visual summary of that. We have, some curve, and we're going to take that curve, we're going to partition the thing. So here's a y value, here's another y value. We're going to partition, and then here is a width. If I take this width and multiply it by one of these heights, I get the area of one rectangle. Okay. And again, if I start the rectangle off to the left, since this function is decreasing, this rectangle will be an overestimate. On the other hand, if I start the rectangle off here, off for the right, function is decreasing, right rectangle, underestimate. Okay? All right. So, in order to get a precise value for the area between the function and the x-axis, we need an infinite number of partitions. We need a very small rectangle width. And if we just keep doing this and doing this and doing this forever and ever and ever, then our estimates for the area will get more and more precise and more accurate. Okay, and so yeah, let's think about what we're doing. Okay, so the area is approximately, okay, and what we're doing is we are adding. So this is a Greek letter sigma. And it literally just means add, okay? We're going to start from the first rectangle, and we're going to end with the last rectangle, which we're calling big N, okay? And it's a rectangle, so it's literally x times y, okay? You take an x value, multiplying by the y value, and that's it, okay? Now I am going to change these symbols ever so slightly, just so we understand better what's going on. Okay, so the first thing I'm going to do is instead of x, it's actually a width. It's actually the change in x. Okay, and y is actually just going to be f of x. Remember, y is a function of x. Okay, and so we wind up with the area is approximately the sum from I equals 1 to n. And then we get f of x sub I, the ith x value, and then multiplied by the width delta x sub I. Okay. So, for example, if we look over here, for example, the width of this rectangle is less than the width of this rectangle. So, basically, this would be like delta x sub 1, this one. And this one would be something like, however many we got here, this would be something like delta x sub 5. Okay, so as you can see here, this is just, the reason these are different, the reason this is delta x1, delta x5, once again, is just because these widths are different. Okay. And in AP, it is common for problems to have uneven widths. That is actually more common than the other case, which is even widths. So please keep that in mind when you're doing approximation problems like this. Anyway, okay. So I hope that what I was saying just a little bit ago makes sense, that if we have more and more rectangles, we get more and more precise. Okay. So how can we change this from an approximation to something exact? Well, we do this. We literally take an infinite number of rectangles. So we do this. We take the limit, and again, we want an infinite number of rectangles. So we literally take the limit as n approaches infinity. Remember, n is the number of rectangles, okay? So limit as number of rectangles approaches infinity. And then what are we adding up? We're adding the area of these guys, okay? So like this. So here we have multiplication, and then we're adding, okay? And then we're taking a limit, okay? So fundamentally, what we have is this. We have integration. What is it fundamentally? Fundamentally, it is a limit of sums, okay, sums. So here's the limit part, here's the sum part of, and each piece of the sum, look here, each piece of the sum is a product. Limit of sums of products. That's what integration really is. It does need to be this type of limit. Either the limit as n approaches infinity, or the limit as the width approaches 0. Okay. So this is the exact definition of integration. Okay. Now the only thing we really got to work out is what's up with n here. Okay, what is up with n? Okay, and because the idea is this. Okay, let me come down here. Let me make a graphical guy here. So here's my XY grid. And anytime I do an integral, anytime I calculate like an area, anyway, let's say I have something like this. Okay. There's always a starting and ending spot. So let's say here's x equals a, and let's say here's x equal b. So we start at a and we end at b. So in other words, the way we would write this down is we would say the integral from a to b of whatever the function is, dx. And that would give us what we have here exactly. Okay, now, there's no n here. Okay? So where does n come from? Okay? Well, here's how that works. Okay? This is for the case of even widths. Even widths only. Okay? And that is what I'm getting ready to show you here. So even widths, we want to make each width the same. Okay? Something like this. If we have even widths, then these are related by the following, okay? The width, which is delta x, is b minus a over n. Okay? So this is how the width the limits of integration, so A and B are the limits of integration, and the number of rectangles. This is how they are related. Okay, so delta x is b minus a divided by n. Okay, so you can think about putting that here. Delta x is b minus a divided by n. Okay, so that's basically what's going on. Okay, so partitioning, we need an infinite number of rectangles to be perfectly accurate. Otherwise, it's an approximation, and if it is an approximation, sometimes we're going to have an overestimate, sometimes an underestimate, so on and so forth. All right. Okay. So yeah, so that's an explanation of what integration is. Next videos, we're going to have some examples.